So thank you so much for the kind introduction and giving me a forum here to talk about what I think is an incredibly timely and important topic that clearly you value is reproducibility. And so I'm going to talk about what I would call the research chain of evidence and how reproducibility fits into this picture of our scientific practice. So first I'm going to talk about the chain of evidence, which is usually a concept that we hear about in the legal and the forensic field. And I'm going to relate that to what we do in science, because we have the exact same concerns as the legal and forensic fields. I'm going to talk about two related but distinct concepts that people often kind of, may confuse for one another: reproducibility and replicability. And what are factors that play into these things, and how do they differ from one another? And then we're going to talk about understanding what are potential risks to reproducibility, and what are some strategies that we can use to kind of mitigate these risks to reproducibility. And then I'll talk a little bit more about building a reproducible workflow and what tools are available to assist us in our work. So I'll try and keep an eye on the chat. I don't want to, talk at you this entire time. Hopefully we'll have some time left over for a lively discussion at the end. But I'll feel free to ask questions or stop me at any time if you'd like to discuss things further. So I am, as you said, I'm a statistician. I'm not a lawyer. So, but I have seen a fair amount of law and order. So what is the chain of evidence in the court of law? Well, whenever something is being used to establish the culpability of somebody, something is being presented as evidence of guilt or trying to convey reasonable doubt, we want to know who obtained this evidence. Where did they obtain this evidence? When was it obtained? And under what circumstances? Once somebody collects this evidence and tags it and identifies this information, it may be passed off to somebody else. So we want to know, for each step in the process, who had this evidence in their possession? When did they first see this evidence? And what did they do with this evidence? So, evidence is collected. It may be stored somewhere. There may be techniques that's used to kind of preserve evidence so that it won't degrade over time. It may be transported to trial and presented. And then in some cases, things may be returned to their owner. But why should we as scientists care about this concept of the chain of evidence? Well, the entire reason that the chain of evidence exists is that we want to make sure that whenever there's handling an interpretation of evidence, that it's done in a way that allows the full evidentiary value of a piece of evidence to be appraised and criticized and discussed. So we want to make sure that our evidence that's being used to determine if somebody's culpability for a crime is able to be given a fair interpretation and avoid the appearance of impropriety, that everything was done according to a set of standard practices. And the thing is, we as scientists have these exact same concerns, only we use just slightly different language. We refer to, instead of evidence, we talk about data. We want to make sure that data were handled and interpreted appropriately, and avoid we have these same concerns about the appearances of impropriety. So if you look at those steps from the legal and forensic kind of chain of evidence, we just have kind of some different names and maybe a few additions here or there. So in addition to collection, we may have data entry if you're collecting data on handwritten forms or CRFs. Data may be entered into a database, either manually, or if you've got electronic data entry, that collection is data entry. Instead of preservation in terms of like physical preservation, we may have backup, like cloud backup services. Rather than transportation, we may talk about data sharing, and there's services for that, how to securely and auditably share data. We have presentation of data, but instead of in the courtroom, it's in journals and in posters and things like that. And instead of returning evidence to the owner, we may talk about archiving of data. And some parts of the data may be destroyed, namely things like identifiers to protect the confidentiality of research participants. So, but for the most part, you see a strong relationship here. And again, the entire concern is about the transparency and accountability of the scientific process. We want to make sure that when people are reporting something in the literature, that everything that they're reporting, we are able to assess whether they are reporting this as the study was actually conducted and as the data was actually analyzed. And we want to make sure that in the case of if there's any questions, that there's sufficient information necessary to reproduce all of the reported results. So that in the case of, let's say, potential conflicts, that we can actually go back, revisit, and reproduce a particular result from the original data. And this is key to the appraisal of scientific merit. We want to be able to make sure that, that what was done matches what was in the protocol, and what was done in the analysis phase of the study matches what was actually reported in the literature. This is also key to actually correcting the scientific record. So there's cases of times where we need to go back and correct the scientific record that we'll talk about. And reproducibility is basically what allows us to identify what went wrong and how to potentially prevent these sorts of errors from occurring in future studies. But importantly, this doesn't guarantee the validity or accuracy of results. So you can have an analysis that may be technically flawed, but is something that can be reproduced. So that's one thing that we need to distinguish, is just because something, we have a chain of evidence of built up, that doesn't necessarily mean that something couldn't have gone wrong during the process. This just allows us a tracking system to potentially identify where things might have gone wrong. So you may see this quote attributed to various different people. So I'll leave it unattributed, but it says that the definition of insanity is doing something over and over and expecting a different result. However, if you've worked in science long enough, I'm sure this has happened to all of us, that you try and reproduce something that you've done earlier, and then all of a sudden you get a different answer than what you did previously. It's kind of every one of us our worst nightmare of having something that came up differently than what happened the first time around. So here I'm going to talk about some cases where the scientific record needed to be corrected for various different reasons. So some of you may be familiar with the Potty and Nevins scandal, which was basically kind of like the promising the holy grail of personalized medicine and cancer, of being able to identify promising therapies and target them individually using microarray data. And this has actually gone from the bench to clinical trials when there were two statisticians, Baggerly and Combs, I believe they were at MD Anderson, who tried to reproduce the results that Potty and Nevins had published, but they just couldn't get the results that Potty and Nevins had actually put out there in the literature. And so they began investigating and interacting with the researchers over the course of months in order to try and figure out why they weren't getting the same things that were being reported. And eventually it came out that there was a student in the lab that reported some concerns about how data was being handled. Perhaps the administration didn't treat these as seriously as they should have. And it ended up that the reason these results couldn't be replicated is both a series of errors and then also intentional manipulation of the data. But it was only through the process of trying to reproduce these findings that all this came to light. So had, Baggerly and Combs not tried to reproduce this, we might have not identified this situation when we did. And this is one of the worst cases of scientific misconduct in history. It resulted in halted clinical trials and lawsuits. This is kind of a nightmare scenario that reproducibility played a key role in identifying something early in the process before it had a chance to go further. But, usually when things happen in the scientific literature, it's not this nightmare scenario. A lot of the things that happen are unintentional errors. Science is a human enterprise, and we're all, fallible creatures that make mistakes. And so what about unintentional errors? These are probably far more common than cases like the Potty and Nevins scandal. So another example is something like the Reinhart-Rogoff scandal. These are two economists who are studying the relationship between sovereign debt and GDP growth. And what they had found that higher sovereign debt was associated with shrinking economic performance. And these were used to kind of bolster, these were used to evidence that, fiscally conservative policies should be used in times of a financial crisis in order to, increase GDP growth. But all of their data was actually publicly available. And because of their findings, people were skeptical and tried to end up reproducing this. And they, lo and behold, when using the same data and the same techniques that were reported in Reinhart and Rogoff's paper, they were unable to obtain the same results. So what ended up happening when they did kind of the post-mortem of this study is it found that data were being unknowingly dropped. There were potential coding errors in their spreadsheet, and perhaps some debatable use of weighting techniques in how they performed their analysis that really were, when people tried to reproduce the result, all of this stuff came to light. And then when they actually corrected the analyses, that it arrived at a completely different conclusion. And so everything we do, it's not everything makes it outside of a paywall. Not everything makes the news, but people use our research every day in ways large and small. So it's on us to make sure that what we're doing is accurately reported, and that when we do make mistakes, that we identify them quickly and are accountable for that. So the other thing is, please don't use Excel for analysis. This actually happened because they were doing their analysis in Excel. That actually led to the data being unknowingly dropped. There was, I think, even a case earlier this year with COVID data where a similar thing happened, where because of limitations in how Excel handled data, data were being dropped from an analysis, and it led to a correction needing to be made to the scientific record. So it's just another plug for making sure people are using the appropriate tools and not trying to do something that Excel really wasn't built for, and we've got much better tools for. So now we're talking about reproducibility and replicability. What's the difference between these two things? Because colloquially, these kind of mean very, very similar things. People might use those words interchangeably. But from a technical perspective, when I talk about reproducibility, I'm talking about the ability to replicate numerical results from original study materials. So if we have the original study documentation, the original study data sets, and code, we should be able to reproduce all of the tables and figures and numerical results and other things that go into our reports, go into manuscripts, and so on and so forth. So that's what reproducibility is about. So reproducibility is a property of the study materials for a single study, okay? So if we have well annotated code and well organized files and everything like that, it makes it much easier to be able to go through a series of analyses and reproduce all of the things that went into a manuscript. But this just makes sure that things are transparently and correctly reported. It doesn't necessarily mean that they're correct. So you can have an analysis that perhaps there's a coding error in the analysis like Reinhardt and Rogoff, but that could still be a reproducible error. Okay, so just because something is reproducible doesn't necessarily mean that it's free of errors. It just means that you can repeat it again and get the same answer. That answer may be right or wrong. So replicability is more something that we would apply to a scientific phenomenon rather than a study. We're talking about a replicability of a phenomenon across a series of experiments. So this is something that in order to talk about replicability, we need to have multiple experiments, not just one particular study. And we may have what's called an exact replication, where we may go out to an investigator and obtain the same cell lines or the same study materials. We may even borrow instruments or reagents and things like that and try and do exactly as they have done. Or there may be there's a continuum of replications all the way to kind of what are called conceptual replications, where you may be studying a particular phenomenon, but you may change the experimental setting or the population of interest or things like that. So replicability is a concept that can be applied to a scientific phenomenon. Reproducibility is an adjective that we apply to the materials for a particular study. And the replicability is a property of not just the scientific phenomenon, but also the study design. So just because you can't replicate a finding doesn't mean that it's the phenomenon itself is not a real thing. You want to make sure that your studies, your replication studies, are actually adequately powered and designed in order to be able to replicate a finding. You want to actually make sure you have adequate power and precision to detect an effect if it exists, and that we're using reliable measures of the outcomes that we're interested in and valid measures of the outcomes we're interested in. So this is a quote from the Simply Statistics blog that says, if I claim that X causes Y, think sugar causes cancer, my analysis might be reproducible, but my claim may ultimately be incorrect for a variety of reasons. If my claim has any value, then others will attempt to replicate it, and the correctness of the claim will be determined by whether others come to similar conclusions. Then why is reproducibility so important? Reproducibility is important because it's the only thing an investigator can guarantee about a study. So replicability has to deal with a scientific phenomenon and a series of studies, each of which is subject to sampling variability and all these other things that are out of our control. Reproducibility, on the other hand, is something that is up to us. It's something that we don't have to leave to chance, and we shouldn't leave to chance. So reproducibility is one of those things like mom and apple pie in America. It's, you can't be against reproducibility, but nobody is outright kind of against reproducibility, but there's certain things that make us kind of, that can make us use non-reproducible practices. Reproducibility requires a lot of time and sustained effort. And this is something, time is kind of a resource that we're always short on time as academics. We're busy, we're trying to be as productive as possible. And reproducibility is one of those things that it takes a lot of time to both learn reproducible habits, to put them in practice, and make sure that our results are ultimately reproducible. And research is a marathon, not a sprint. I don't think I have to tell anybody about this, you know, and it's highly iterative. So for each project, we're creating documents, we're organizing things, we're planning things, we're doing analyses, and then we may get to a point where we need to go and revise things. And so because of this highly iterative nature of research, and the fact that our data and analyses are increasing in complexity and sophistication, this means that the challenges we're facing right now are very different than some of the challenges we might have been facing a decade ago. And think about how many people have had training about, you know, programming or data management and analysis. These are things that when you're getting a PhD or an MHS or things like that, you may never have a course completely dedicated to good programming practices or good data management practices. You know, how many people, just a show of hands at the little Zoom, how many people have actually had a course specifically on data management practices? Anybody? Okay, so we got a couple. How many have had a course on good programming practices? How many of your collaborators have likewise had those courses? So this is because research is increasingly collaborative. Reproducibility is not just on our shoulders, but it's on our collective shoulders. So not only are there new challenges that we're seeing now that we haven't before, but because we're dealing with people who may not have had these sorts of training, that's another challenge to reproducibility. And nowadays, programming is an indispensable part of research, but it's something that, you know, it takes a long time to learn good programming practices, and people usually develop habits, and habits are very hard to break. We learn from a variety of different sources, and so it's important. Programming is something that's absolutely essential these days, but very little attention is really given until fairly lately in terms of teaching good programming data management practices. And again, you know, research is increasingly interdisciplinary and collaborative, and how these practices penetrate into different disciplines is very different. You know, if you're working in bench science, you're going to have a very different set of courses relating to working with data than somebody who's in epidemiology. And all of us are kind of on this quicksand of this ecosystem of instruments and software that are constantly evolving and seemingly evolving at a quicker and quicker pace. So, you know, think about where software tools were even 10 years ago. We didn't have OneDrive, we didn't have Box. Before Box, it was something called JShare. And then maybe before that, we had network drives. You know, all of these things have you know, considerably changed over the past couple of years, and the rate of change is increasing as time goes on. So this gives us potential threats we have to look out for, like proprietary software, where, you know, once we lose access to a particular piece of software, we may not be able to get back to the original data. Or maybe it's in a format that can't be read by current software. Or maybe we're dealing with a proliferation of different computing and storage platforms. So we had not too long ago the shift from Box to OneDrive. And nowadays there's these, because of, we've got this interdisciplinary research, there are these secure computing environments where we log into a virtual computing session and we're stuck using whatever software we have in that virtual environment. So these are posing new challenges to reproducibility that previously we really didn't have to consider. So this is a quote I love because it really kind of shows the other side of reproducibility, that it's not just something that's integral to to scientific integrity, but it also makes us better researchers. So it takes some time, or it takes some effort to organize your research to be reproducible. We found that although the effort seems to be directed to helping other people stand upon your shoulders, the principal beneficiary is generally the author herself. That is because time turns each one of us into another person. And by making an effort to communicate with strangers, we help ourselves to communicate with our future selves. So we're constantly dealing with this iterative, highly iterative workflow and juggling many different projects. So if we want to actually be as productive as possible, we need a way to organize things and work so that when we pick up a project in 6 months, 18 months, or potentially years down the road, we have some idea where we left off and how things work. So if anything ever, we ever need to revisit anything or ever need to expand upon what we did previously, that we're able to do that easily. So it's not just something that's crucial to the scientific literature, it's also important for our own productivity and sanity as well. So let's think through what goes on in research. We have a phase of collecting the original data. And then we may have a phase where we go through cleaning and renaming and reshaping and deriving new variables and creating new data sets from this original data. Then we may analyze the data. We may define an analytic cohort based on certain criteria. We generate some tables, some figures, we do some modeling, we check our modeling and get some predictions and results that we want to report. And then we kind of run this gauntlet of review. Maybe we review things in our lab amongst our peers and go through things and maybe elicit some feedback from them. And that may send us back to maybe rethinking how we defined our analytic cohort originally. Or maybe we need to create some new tables and figures in order to kind of address those concerns. Maybe we're working with a research consortium. So after that, we have another phase of external review. And so it may be that we have to present to a research consortium before that goes out to peer review. And then when we submit to publication, hopefully our reviewers have helpful comments that may be thought-provoking and help make our research better. So at each one of these steps, it might send us back down to these other steps of how we define our cohort and what data we're working with, or even identifying issues that need to be addressed even in an earlier phase. So there may be additional sensitivity analyses or other supplementary material that need to be created at each step of this process. And this is just within one particular research project. or we're typically working on multiple research projects and multiple collaborations. So we need to be able to keep on top of this so that we're able to kind of respond to this highly cyclical nature of research. And let's think through what are potential risks to reproducibility. So we talked about proprietary formats and software. And another thing to think about is something called software as a service. So it used to be that, you know, when you bought a piece of software, it was like, you know, buying an appliance. That appliance is yours, and nobody's gonna, you know, come to your house and take your dishwasher after a year. But nowadays, like, you're usually buying a license to software. And at some point, that license may expire and you no longer have access to that software. So it's important to kind of think about, be vigilant about what are our software licenses? Are they good for the lifetime, or are they only good for 5 years, 1 year? What happens after that time expires? And if there's any instruments that save data in a particular format, is there a way to kind of jailbreak it into another format that can be read in any software, such as, you know, CSV files or other types of formats that aren't restricted in terms of what programs can use them? Then there's also the availability, versions, and compatibility of software. Software might not always get along, so as software becomes updated, there may be conflicts between different versions of software. And so these are things that we need to be aware of. And these are some ways we can kind of combat this. Are number one is archival networks. So there's archival networks for R and other statistical software package. So if you need a particular version of R or one of its libraries, we can go retrieve that in order to reproduce an analysis. But in order to understand what version of the software and package we need, we also need to document what version of these things we're using in case we actually need to go back and reproduce that result. Then there's also the issue of personalities, priorities, and values in research. You know, the motto of academia is publish or perish. And like we said, one of the big things about reproducibility is it takes a lot of time. It takes a lot of effort, not only in acquiring these skills and these habits, but also in putting them into practice. So it's when we have such a strong pressure for productivity, it's important that, number one, we educate our collaborators on what are good research practices. Number two is that we communicate what are, why should we be doing things in a certain way, and agree upon how we're going to do things at the outset, and align our incentives so that everybody's on the same page. And that way we avoid the perception that people are you know, taking too much time, or that this is kind of an unnecessary burden or unnecessarily slowing down progress. But this is the personalities, priorities, and values in research. This is always a struggle. The other thing is we're dealing with interdisciplinary collaboration. So if you're sharing data with people, people may accidentally overwrite or modify data or accidentally move things. So we can, by setting up our file permissions and our structures, we can potentially mitigate some of these risks. And a lot of tools, thankfully, a lot of tools these days allow you to look at who made changes to files and eventually roll back to earlier versions. So if there ever were a particular change, you can track and see who did this change, when was this done, and then actually look back to earlier versions. So again, this helps us create this same sort of analogous, chain of evidence like we had in the law enforcement example. And it's important to have a coherent strategy for reproducibility and make sure that it covers the entire research life cycle. So from starting with when you're designing a study, you have a data management plan or DMP. And then when you're collecting data, making sure that you're collecting data in a way that is auditable and transparent. Many databases allow you to track each individual change of a record to an individual at a particular point in time. So you can see what was changed by who, when. But this needs to go beyond just the data collection step, but also when we're working with data outside the database. And in that case, we need to think about our data and our documentation and code. So everybody has a part in making sure that a project has reproducible results. Everybody from PIs to data managers and statisticians. So it's important that everybody kind of knows their roles and agrees upon plans for how to proceed in a project. So for those that aren't aware, the ICTR put out a best practices in data management website that actually breaks down the different phases of research, from design to conduct to analysis to archiving, and breaks things down by what are the different roles and what are their responsibilities for data management planning. So this is an excellent starting place for familiarizing ourselves with our responsibilities. But there's also the analysis part after we get the data out of a database that we need to think about. The data management plan can be helpful here, but that's usually a very high level thing. So we need some standard operating procedures in place that are a little bit more granular to kind of tell people, how do we store things? How are we going to name things? Those sorts of things that can help projects be more reproducible. And with any plan, it's important to not just make a plan and then put it somewhere, making sure that people are using it and reevaluating it, because sometimes we've got a constantly changing landscape of software and services and things like that we need to keep an eye on. So it's important that we reevaluate and see how things are working and change them if they're not working. And again, everything is in constant flux. So we need to have these be living documents that change with a study. Another important thing is investing in reproducibility. So this involves making sure people are appropriately trained, that they have all of the tools necessary to be reproducible. And then, not just, talking till we're blue in the face, but actually putting these principles into practice and holding ourselves accountable to making sure things are reproducible. The good news is that many tools are free, but there's also the very American expression of time is money. So that even though the tools are free, training people, implementing them, and making sure that we're checking and reevaluating to make sure that we're doing things the right way, that takes time. So I'm going to talk about the primary data as the data we originally collect. So this could be paper CRFs that are entered into a database, or it may be data that we're capturing using an electronic data capture, such as REDCap or some other data collection instrument. Whenever we modify any part of this primary data, we save it separately as what I'll call secondary data. So whenever we do anything to it, renaming, sorting, changing, creating new variables, or modifying values, all of that it becomes secondary data. And an analytic data set is just the variables and values we need to reproduce a particular analysis. For any particular research project, we may actually have a couple analytic data sets, but the number of primary data sets may be in the dozens or hundreds, sometimes even thousands. And going along with our data is the code and documentation that help link the original data to the results we're producing. And so I'm going to talk a little bit more about this later. So primary data, it's important that we never modify that and store that separately so that we prevent data from being accidentally modified. Because if somebody modifies the original data, that's something that is very, very hard to track down. And it's important that we instruct people to do all of the modifications done using programs for a couple of reasons. You know, if we have the same input and the same computing environment, that'll give us the same output. It also limits the potential scope of errors. We want to make sure that our code is well documented, that we know not just what the code is doing, but also why the code is doing it. Making sure that when we define new variables, documenting the decision why we chose to define things in a particular way, because eventually we're going to have to convey that to others. So it's important that we've got kind of an audit trail of what decisions were made when and why. And this is where version control enters the picture. So if we're writing code and doing things to make things from our original data, it's important that we know who modified the code and when. So you can think of this as like a track changes in Microsoft Word for code. This allows us to do a number of useful things, including recover previous versions, so we can see the difference between a previous result and a current result. And then it's also important to have other practices like date stamping and version codes so that we can understand what are the impacts of modifications and then what pieces of code work together. So if we're building a pipeline to get from our original data to our results, we may have various different things that change during the course of a project. So it's always important to be able to pick out what's the latest version of things, what are the different versions, and what pieces of software all work together. So if we see something like a file that's just named demographics, we might have no idea what software produced this, what version of the data this is. So if we're collecting data in, let's say, a clinical trial, the state of the data is constantly changing over time. So by giving specific names and date stamps and version codes, it allows us to see not only descriptively, what is this data, what's the version of the code used to produce it, and what's the temporality of the data. So I won't go through all of these, but these are various different reasons why version control is important. And this is extremely important with a highly cyclical and iterative nature of research, because we're constantly making changes to things and then sometimes undoing those changes later. But version control allows us to see what was changed when, by whom, what were the decisions made, and what was the thinking behind them. There are also utilities like diff that allow you to see the changes between two different versions of a file. So here's an example of a diff between two text files. So here you can see the line number, line 69, the red line above is what's being deleted, and the green line is what's being inserted in a new version of a file. So we can see what's being added, what's being changed at each point in the process. And there are commands for this in any operating system, whether it's Windows or OS X or Linux. There's a number of utilities for this. So when we're creating multiple versions of a file, it's important to be able to track, what's the data that went into a particular analysis. And this is where something called a file hash can be something very useful. It allows us to kind of create a fingerprint for this file. So this is something that's very sensitive. So if I make any modifications to a file, it's going to change the file hash, which is basically like a string of characters. So whenever I make any tiny modification, it's going to change the file hash, but this doesn't tell us what about that file changed. If, let's say, we want to know what changed between two different versions of a file, there's various different utilities and software that allow us to look for, were columns added or removed? Were there changes between values? Are the data types the same between two different versions of a data set? Are there changes to the labels and so on and so forth? So between, file hashes and these other utilities, we can be able to see how a particular change in the data translates to a particular change in results. And then we've got cloud utilities, which allow us to see, who modified what and when and revert to earlier versions. So this allows us to do something kind of similar to a diff, but with more complicated files. But it doesn't give us this kind of nice direct summaries of the changes like a diff does. And now just some quick practices that help make research projects reproducible is having file and naming and organization standards. When you're looking at something 2 years down the road, it's a lot harder to remember what you were doing. So in my opinion, keystrokes are cheap, time isn't, especially when you're on a deadline. So I'm usually somebody who's for longer descriptive variable names, because when you're going back to a project, it makes it easier to see what was being done. What is it? What does it represent? What does it do? Where does it belong? So it makes it easier to see the organization and understand the flow of a research project. This makes it easier to understand, use, and reuse. And particularly, it makes it easier to collaborate with others. So this allows us to put a lot of information in files and directory names and variable names that allows us to understand what was being done. So if we name our files appropriately, this allows us to kind of, when we sort alphabetically, we know exactly the order in which things need to be run. By giving them specific names, we know what things are doing, processing the original data, reshaping, and then maybe making an analytic version of a data set. We know that all of these things play nicely with one another, and then what version of the data they're using. So again, just right from the file names, it makes it easier to be able to reproduce a particular result. And then having these things that appropriate names to convey information effectively. So, if we just have age in a regression, what does that mean? Age when? Is that age in year 1, in year 5? Who knows? But by naming things effectively, we can convey different things like this is age at baseline centered at 65 years of age or scaled to a particular increment of time, and so on and so forth. And this also makes it easier to use wildcards and suggestions. So there's a lot of benefits to having these sorts of naming and coding conventions aside from reproducibility. It makes us more productive. And so it's also important to consider a style guide. This is the Tidyverse style guide for R, which I highly recommend, but there's other style guides for Stata. So just to kind of wrap things up here, so hopefully we can get into discussion. Reproducibility and replicability are different. Reproducibility has to deal with a particular study's materials that allow us to reproduce a result from the original materials. Replicability is about scientific phenomenon. If we have appropriately designed and conducted studies, we hope to be able to replicate a finding across these studies. But again, reproducibility is under our control. Replicability is not, because of sampling variability amongst other factors. So reproducibility is hard, but worthwhile. There's transparency and accountability are things that help us contribute to the scientific literature, but there's also tangible benefits for the individual researcher themselves, making their work have greater longevity and reusability. Programming is an essential skill, so to make sure that people are investing in it, because again, languages change with time, practices change with time. This is something that we need to keep on top of. And that these are our habits that we need to acquire, and human beings are generally not good at that. So it takes not only the training to learn these practices, we need to put them into action, and then have the discipline to hold ourselves accountable, all of which costs time. And that's something that we need to convey to our colleagues, that you know, while this may cost time, it's an upfront cost, but it's very, very, very much worth it in the long run. And that's why it's important to have a plan in place and have that discussion early on, because we're dealing with interdisciplinary and collaborative projects. And it's important that we don't just, you know, talk about reproducibility. The hardest thing is walk the walk, is holding yourselves and others accountable. But again, it's not just something that's beneficial to the scientific literature. It's beneficial to you as a researcher in terms of your productivity and also the quality of your research.